Chapter 2 is concerned with the solution of Fredholm integral equation of second kind with degenerate kernel. This chapter is divided into 3 modules. This is the first module of chapter 2. In this module, we shall learn what is called a degenerate kernel and how to solve Fredholm integral equation of second kind with degenerate kernel. And we shall summarize all the results in form of a theorem called Fredholm alternative. Now, the Fredholm integral equation is given by equation 2.1, where the kernel kxt is degenerate or separable, and we shall solve this equation 2.1 for degenerate or separable kernel. Before going into the solution, we rewrite the integral equation 2.1 in operator form as given by equation 2.2, where capital I is the identity operator and capital K is the linear operator which is defined by the relation given by equation 2.3. Now the question comes, what is called the degenerate kernel? A kernel kxt associated with the integral equation 2.1 or 2.2 is said to be degenerate if this kernel kxt can be expressed as a finite sum of product of two functions aix and bit as given in the equation 2.4. Here aix and bit I equal to 1 to n are two linearly independent finite set of continuous functions on the closed interval ab. Now the degenerate kernels are also called the separable kernel. Now we substitute the kernel kxt from equation 2.4 into the given integral equation 2.1. So here, after substitution of kxt, we will have in the second term a summation and a integration. We now interchange the summation and integration, and this is possible because the functions involved are continuous. Doing this, we can write phi x in the form as given by equation 2.5, where gamma I is given by the integral 2.6 and gamma I involves the unknown function phi t, so it is unknown. If this unknown constants gamma I can be determined somehow, then the solution of integral equation phi x, which involves this unknown constant gamma I in equation 2.5, can be known. So we are now to determine gamma I. We substitute phi t from equation 2.5 into equation 2.6. Doing so, this gives the system of linear equation 2.7. Here I also varies from 1 to n. In 2.7, lambda is the parameter of the integral equation. Beta I and alpha ij, they are the known functions given by equation 2.8. Now we shall solve this system of linear equation 2.7. So the solution of integral equation has been reduced to the solution of the system of linear equations given by equation 2.7. The system of linear equation 2.7 can be expanded to write in the form this. So we can write this system of linear equation in matrix form as given by equation 2.9. Here beta vector is the column vector consisting of the functions beta 1 to beta n, and this C vector is the column vector consisting of the unknown functions gamma 1, gamma 2 up to gamma n, and the matrix B is given by I minus lambda A, where I is the identity matrix of order n cross n and A is the square matrix whose elements are known functions alpha ij. Now we proceed to solve the system of linear equations given by equation 2.9. The unique solution of this system of linear equation will exist if the matrix B is non-singular. If the matrix B is non-singular, that means B inverse will exist and the corresponding homogeneous system given by this equation has only trivial solution. So if B is non-singular, then we can obtain the unique solution of the system of equation 2.9, that is, we shall find out gamma I, the unknowns, by using Cramer's rule, and this is given by equation 2.11. Now in equation 2.11, the function d lambda denotes the determinant of the matrix B. Since the matrix B is non-singular, so this determinant is not equal to 0. Now the values of lambda for which makes this determinant d lambda not equal to 0 can be obtained by equating d lambda not equal to 0. So for those values of lambda for which d lambda not equal to 0, we can use the Cramer's rule to find out the solution gamma I as given by equation 2.13. 2.13 is the short form of equation 2.11. Here capital Dji is the cofactor of jith element of the matrix B, that is I minus lambda A. So once gamma I is obtained, we can find out the solution of the integral equation given, which is given as given by equation 2.14. Now in equation 2.14, beta j is the known function which is written as an integral of two known functions. If we substitute beta j from first relation of equation 2.8, then we can write phi x in the form as given by 2.15. So the phi x is the solution of the given integral equation with degenerate kernel, and in equation 2.15, if we write the expression in the first bracket as the function r, capital R, x t lambda, then this phi x in equation 2.15 can be written as given by equation 2.17. So this is the unique solution of the given Fredholm integral equation with degenerate kernel. The function capital R x t lambda is called the resolvent kernel of the integral equation 2.1. So phi x from equation 2.17 has been obtained as the solution of integral equation 2.1 with degenerate kernel when d lambda is not equal to 0. That means for those values of lambda which makes d lambda not equal to 0. For those values of lambda, the corresponding homogeneous integral equation given by equation 2.18 with the degenerate kernel has only trivial solution. So far what we have obtained we can summarize in form of observation 2. We observe that if the homogeneous Fredholm integral equation of second kind 2.1 with degenerate kernel 2.4 has only trivial solution, then the corresponding non-homogeneous Fredholm integral equation of second kind with degenerate kernel has unique solution as given by relation 2.17. So far we have obtained the solution of Fredholm integral equation of second kind with degenerate kernel when the matrix B is non-singular. That means the determinant d lambda not equal to 0. So this gives values of lambda for which the unique solution of Fredholm integral equation of second kind is obtained. Now we consider the case when the matrix B is singular. That means the function d lambda is equal to 0. When the matrix B is singular, then the homogeneous system of linear equation corresponding to 2.9 given by equation 2.19 will have non-trivial solution. Now, from the theory of linear algebra, we know that either the system of linear equations given by equation 2.9 is inconsistent, that means it does not have any solution, or it has got non-unique solutions. The non-unique solution of the system of linear equation 2.9 will exist if and only if any solution given by the xi vector of adjoint homogeneous system of equation given by equation 2.20 satisfies equation 2.21. Here bar denotes the complex conjugate, that means beta I bar is the complex conjugate of the known function beta I, and the matrix B star is given by I minus lambda A bar transpose as given by equation 2.22. Now, we note the expression beta I from equation 2.8, and then we substitute beta I in the equation 2.21 to obtain this equation. Now, writing psi t as given by equation 2.24 as this summation, we can alternately write this equation in the form given by equation 2.23. You must remember that ft is the forcing function of the integral equation which is known. Now, B star is given by 2.22 and xi is the solution of equation 2.20, and xi is related with the function psi t as given by 2.24. So, we shall now see what equation this function psi t satisfies. So, from relation 2.22, we see that xi satisfies this equation. So, expanding this equation, we can write the equation 2.25. Next, we multiply equation 2.25 by the function b I bar x and sum over I from 1 to n to obtain the relation given by this expression. Now, you must be remembering that alpha ij is the known function. So, taking alpha ji bar and substituting in this relation, we can write this relation as given by this expression. We know from equation 2.24 that psi t is given in terms of xi. So, this expression can be written as in terms of psi as given by equation 2.26. This equation 2.26 satisfied by psi x is the adjoint equation of the homogeneous equation corresponding to given integral equation as given by this. That means equation given by 2.26 is the adjoint equation of this equation. So, we observe from whatever I have told that if the homogeneous integral equation with degenerate kernel given by this equation possesses non-trivial solution, then the corresponding non-homogeneous equation 2.1 is either inconsistent or possesses non-unique solution, and this non-unique solution will exist if and only if the forcing term satisfies the relation 2.23, that means this relation, where psi t is the solution of adjoint homogeneous equation 2.26. We shall now summarize the observations given by observations 2.1 and 2.2 in the following important theorem, which is known as Fredholm alternative. We now state this Fredholm alternative in form of theorem 2.1. Let phi x satisfies the following Fredholm integral equation of second kind as given by equation 2.27 with degenerate kernel kxt given by equation 2.28, where aix and bit are two linearly independent continuous functions on the closed interval AB. Then either the integral equation 2.27 possesses unique solution phi x for every continuous function fx on the closed interval AB, in which case the homogeneous integral equation given by 2.29 corresponding to equation 2.27 possesses trivial solution. Or if the homogeneous equation 2.29 possesses non-trivial solution phi naught x, then the non-homogeneous integral equation 2.27 is either inconsistent or possesses non-unique solution. It will possess non-unique solution if and only if fx satisfies the condition given by equation 2.30. Here the continuous function psi t is the solution of adjoint homogeneous equation given by equation 2.31. This theory is known as Fredholm alternative. So, in module 1 chapter 2 we have learned how to solve Fredholm integral equation of second kind with degenerate kernel, and we have summarized what we have learned in this module in form of a theorem which is known as Fredholm alternative.